We're gonna carry on with the infinite square wheel. This is a different example, a bit more complicated, but it's doable. A particle in the infinite square wheel has its initial wave function and an even mixture of the first two stationary states. So this is our wave function psi of x and 0, 0 is the time, is equal to some normalization constant times the first quantum state plus the second quantum state. So it's a linear combination of both. We're gonna first normalize the wave function, and then we're gonna find it in terms of time, and then we're gonna find its probability density. This is psi star psi, this guy here, and then we're gonna compute the expectation value of the position. Keep in mind that we're gonna use a formula called Euler formula. Let me pull it here. If you recall from before, Euler formula is I to the e to the I theta is equal to cosine of theta plus I sine theta. Okay, so we're gonna use this formula, and first we're gonna normalize psi. So normalizing psi is you take the magnitude square of sine and you set it equal to 1. The magnitude square of psi is basically you take a square, right, times psi 1 complex conjugate plus psi 2 complex conjugate times psi 1 plus psi 2. We're gonna distribute, we get the normalization constant magnitude squared times psi 1 star psi 1 plus psi 1 star psi 2 plus psi 2 star psi 1 plus the last term psi 2 star psi 2 star psi 2, close brackets, and then we're gonna integrate this guy and set it equal to 1. So 1 is equal to the integral of these guys dx, these guys, right? So remember what we said when we integrate psi star psi and this the quantum states are equal to each other. This is the Kronecker delta. This is like psi m. Remember psi, like psi m psi n. When the m and n equal, this is 1. When the I and m are not equal, this is 0, right? So here we get 1, here we get 0 plus 1, and that's the integral. So we have 1 equals 2 times the magnitude square of a. Solving for a, we get a to be equal to 1 divided by square root of 2, which makes sense, right? Okay, so this is part A. Part B, we're gonna have to find the wave function in position and time. So finding the wave function here, we have 1 divided by square root of 2, that's a, times psi 1. Remember what's the solution for the time? It's I to the e to the minus I times E 1 times T divided by H bar plus psi 2 times E to the minus I E2 times time divided by H bar. But we know that E sub n divided by H bar, this is equal to n square times omega. Why? Because I say so? No, because we're gonna define omega to be E sub E sub n divided by H bar n square. So we're gonna define omega this way. So with this in mind, we have this psi of x and t. We have this to be equal to 1 divided by square root of 2 times square root of 2 divided by a times the sine of pi divided by a x, because n is 1, times e to the minus I omega t plus sine of 2 pi divided by a x times e to the minus I omega t. Simplifying a little bit further, we have psi of x comma t be equal to 1 divided by square root of a times e to the minus I omega t times sine of pi divided by a times x plus sine of 2 pi divided by a x times e to the minus 3 I omega t. There you have it. This is our wave function in x and t. So now we have to find its probability density, which means we're gonna have to find the magnitude of psi of x and t square. Or even better, we're gonna have to find psi star psi, which is equal to 1 over a, remember it's square, so now we have 1 over a times sine square of pi divided by a x plus sine of pi divided by a x times sine of these are the cross terms, right? 2 pi divided by a x times e to the minus 3I omega t plus e to the 3I omega t plus the last term, which is sine square of 2 pi divided by a x. This middle term, the cross terms, this guy over here, from this plus sign to this plus sign, I simplified it using some exponential properties, but you know, you can do it or you can take my word for it. I'm gonna simplify this equation a little bit further. We have 1 divided by a times the first term, sine square of pi divided by ax, plus the second term, which is sine square of 2 pi divided by a. This is the second quantum state, x, plus the cross terms, and the cross terms simplify to 2 times the sine of pi over ax times the sine of 2 pi over ax times the cosine 3 omega t. And this, my friends, is the probability density of our psi function. There you have it. Next, we're gonna find the expectation value of x. It's a bit heavy in math, but it's very doable. Expectation value of x, if you remember, we're gonna integrate our psi star or complex conjugate. Basically, complex conjugate means that you're gonna take every imaginary term in your equation and turns it into negative. So if it's negative, you turn it into a positive, right? X times psi of x and t dx. So equals 1 over a times the integral from 0 to a x times times what? Do you remember what? Our psi star psi, or the probability density. We just found this one. Sine square of pi divided by a x plus sine square of 2 pi divided by a x plus plus 2 times sine of pi divided by a x times the sine of 2 pi divided by a x times cosine of 3 omega t dx. So this is what? This is 3 integrals, yeah? This is the first integral, the second integral, and the third one. So the first integral, we're gonna break it into 3, okay? The integral from 0 to a of x sine square of pi divided by ax. This is equal to x squared divided by 4 minus x sine of 2 pi divided by a x divided by 4 pi over a minus cosine of 2 pi divided by ax divided by 8 times pi over a to the second power. Then we're gonna integrate from 0 to a. Doing the integration and simplify, we get a squared divided by 4, which is also equal to the second integral, the integral from 0 to a of x sine square of 2 pi divided by a x dx. So here we go, we knocked off two integrals in one shot. So now we have to integrate the third part, which is the integral the integral from 0 to a x sine of pi divided by a x times sine of 2 pi divided by a x dx. What happened to the cosine of the negative 3 omega t? It's a t function, so we treat it as constant, right? So we're gonna use a trig identity here. Sine will switch to cosine minus cosine, so we have 1/2. This is from the trig identity. The integral from 0 to x of x times cosine of pi divided by a x minus cosine of 3 pi divided by a x. One is addition, one is subtraction. Dx. Okay, so this gives us 1/2 times a square divided by pi square cosine, because this is like x cosine x and then x cosine x again, so this is easier integral than the one above. Pi divided by a x plus ax divided by pi times the sine of pi divided by ax minus a square divided by 9 pi square cosine of 3 pi divided by ax minus ax divided by 3 pi times sine of 3 pi divided by ax. And finally we're gonna integrate from 0 to a. So doing the putting the limits and simplify, we get we get the expectation, not the expectation value, this integral alone, minus a squared divided by pi squared 1 minus 1 over 9. We'll simplify even further to minus 8 a squared divided by 9 pi square. So finally now we're gonna put all these three integrals together. So the expectation value of x equal 1 over a times a square over 4 plus another one of these, a square over 4 plus minus 16 a square divided by 9 pi square times the cosine of 3 omega t, close brackets. Simplifying a little bit further, we get the expectation value of x to be a over 2. See, this is if we have only one stationary state inside our square wheel, right? But then we have another factor, which is 1 minus 32 divided by 9 pi square times the cosine of 3 omega t. So the amplitude of this guy is 32 divided by 9 pi square times a over 2, right? This is the amplitude, which is simplified to 0.3603 times a over 2. So this is the height of the wave function. The angular frequency that's the 3 omega. This is equal to 3 pi square h bar divided by 2 times the mass times a square. There you have it. So this is the expectation value of x. Try by yourself to find the expectation value of p. Okay, it shouldn't be that hard. You just have to take a time derivative of this. Don't forget that now you actually have to do the time derivative, because this is not a constant in time.